Hope you had a great lunch break. I want to talk now about machine learning and how you can apply that to real-time processing. That's a very hot topic I see all the time at many of our customers. So the first question, who of you implemented an analytic model with R, with Python, or any other tooling? Who already built an analytic model? Okay, that's not many people, but that's good. This is a beginner session, so I will introduce you to how to do that and why that's getting very interesting. And therefore, let's begin with the session, and in the end, I want to show you two things today. I want to first show you how you find insights and patterns, which are stored in a historical data store, like Apache Hadoop, for example, or maybe even just a data warehouse or some file system. And then you find these insights, that's the first part. You use analytic models using machine learning to find these insights and patterns. And then you apply these new insights to new events, to do predictions to the future, for cross-selling, for fraud detection, for predictive maintenance. So if you talk about or think about machine learning, it's always important to consider both of these steps. First, you build an analytic model based on historical data, and then you apply these new insights and rules to new events to get an advantage, a business benefit out of that. For that, I have the following agenda for the next 40 minutes, 3 points. First, a very short introduction about what I mean with machine learning and why it's getting so important in every enterprise in the meantime. And then I will show you how to build the analytic models and how to apply them to real-time processing. I will show a few live demos with R code, with TensorFlow, with H2O, and also how to apply that to event processing afterwards. Let's begin with the motivation. What is machine learning and big data analytics? Why do we need that today, or why is it coming? This is a great picture which really explains it in one single term in the end. So machine learning allows computers to find hidden insights without being explicitly programmed. And that's completely different from what you did in the past when you write Java code or C# or Ruby or whatever, where you have if-else statements and for loops, and where you explicitly write what the computer has to do with the code. With machine learning, the computer learns what to do. And why do we need that today? Because we have so much different data and unstructured data. And Google, Facebook, and all the tech giants use machine learning, as I will show you in a minute, because you cannot handle it otherwise. And that's basically what I mean with machine learning, that really the computer learns from the data. You don't explicitly program everything. You just bring the data to the computer and it learns by itself what to do with that. That's the basic definition of machine learning. And so let's take a look at a few examples for that. I have some problems with my pointer. So here is the first example. Spam detection, that's 20 years old or so, but it's the best example for starting with this thinking about machine learning. Spam detection is needed for all the different spam, and spam changes all the time. So if you take a look at your inbox, and when you get spam, the text and strings change. And the spam creators are clever, they change some text and do some new images and so on. And the computer has to learn if it is spam or not. This got a lot better in the last year or so. You rarely really get spam anymore because it filters it out very well. And the reason for that is that Google and Hotmail and Microsoft and so on, they have very good machine learning models which train their engine to understand if it is spam or not. And you also help them training with clicking on a spam button to say this is spam or this is not spam sometimes. And therefore you improve the probability of the spam algorithm. And of course here billions of users are doing that, and therefore these spam filters are getting that good. So the next example, it's getting more and more powerful over the years. If you think about search engines like Google or Bing, 15 years ago when you searched, everybody of us got the same result when you searched for a specific term. Today, everybody of us gets a specific contextual term. So everybody on Google from you will see different search results. So it's specific for you about your interests, about what you searched in the past, and all this is done by an analytic model under the hood. You cannot program this for every person to give context-specific rules or so. So the computer has to learn what to send to which person. And why is Google and other search engines doing that? Because also for the advertisement. So they give you the best possible advertisement to make more money with that. And that's only possible if it's context specific to every specific person. And therefore again the machines under the hood have to learn all the information, terabytes and petabytes of data, to make this context specific recommendations. Then if we go to Facebook, for example, today, if you upload a picture with your friends on holiday, if you upload a picture, immediately Facebook asks you who these persons on this picture are. And they make recommendations to you. Is this your girlfriend or is this your buddy? And you click yes or no. And typically, these machines are very good in the meantime. So often the machines are even better than we are. So in picture detection, a human can maybe, let's say, out of 100 pictures, on 98 pictures decide if it's a person or not, and the computer can say it on 99.9%. So the computer is already getting better in recognizing pictures than we as human are. And this is what Facebook is using to detect pictures and analyze the objects on them. And it's not just about the persons, but it's also about the objects there. So for example, if you have a beer in your hand and you're on holiday, Facebook can analyze which beer it is. And therefore, again, they can calculate which advertisement do I send to you. Is it a Budweiser when you're in the US? Or is it another beer or whatever you use and consume? And with that, they can, again, make better advertisements and make, in the end, more money with that. And last year, that was also a big announcement where Google had a machine learning or deep learning algorithm where they bet a professional Go player. Go is a board game which is much more complex than chess. And now we have machines or algorithms which can beat the professional Go players in that by training the analytic models more and more. And so this gets more and more powerful all the time. And for example, I'm directly coming more or less from Silicon Valley. I was there this week. And if you go on the street in Palo Alto or Mountain View, you see the Google driving cars. Or you see Uber in the Bay Area. They introduced carpooling. That means you do not only drive your Uber by yourself, but join other participants to save money with them. And under the hood, it's so complex, and the analytic model has to compute which other passenger do I take with me, so that everything works out, that the people save money, but also that the people are happy because the ride does not have to take too long. And there's so much data you have to consider here, and only the computer can learn that and make these decisions for you. And this is all tech stories from Facebook, Google, Uber, and all these tech giants. They are using this now for 10 years or so, and it's getting better and better. But now this is also coming into the enterprises, into retailer, telcos, banks, everywhere you can now leverage machine learning. And this is what I want to show you today now, how you can do that. And for that you have two parts. You have first to find insights and actions in historical data, to build analytic models, and then in the second part you put that into action for new future events to apply the analytic model. So let's begin with the first part, build an analytic model. In the end, this is really the most complex process of these two steps. Deploying the model afterwards, as we will see, is pretty easy. You just use the algorithm and deploy it to a runtime. But first you have to go through an analytic pipeline to build the analytic model. Let's go through these steps very quickly, and then I will already go to the live demo. So first of all, you have to access the historical data. So many researchers showed, and it's also our experience with our customers, you only really get good analytic models when you combine different historical data sets. So not just the customer information, but maybe some other information, maybe the weather, or maybe some external service, or depending on your use case. You have to add different data sets and correlate them with each other. After you access the data, you have then to prepare the data. That means things like data cleaning, removing duplicates, and so on, and also feature engineering, which means to decide which attributes are the important ones for my analytic model. Often you have thousands of columns and have to decide which 5 ones are the important ones to make the right prediction afterwards. This is data preparation, and you do that before building the model. And this step typically 60–70% of the complete process where a data scientist works on. That's very important to understand. So this is where the effort goes in, and where you sometimes can use some good tooling which can help you there to be more efficient. And after that, after 70% or so of the time already went over, then you can start analyzing the data with some kind of visualization. Either you can directly do it in the coding language like R or Python to do some visualizations, or you use some visual analytics tool like Spotfire, Tableau, Click, or something like this where you can easily play around with the data in a visual environment. And even here already you can again apply machine learning, because these tools under the hood also are very intelligent already. I will show in the demo what I mean with that. But in the end, the goal is that business analysts can even use machine learning without explicitly programming it, so that the tool supports you with that. I will come back to that later. And then you build your analytic model. In the end here we see a simple one, that's a formula. And in the end, a machine learning algorithm, that's the output. It's a formula, typically much more complex, with much more parameters which you have. And then you get your new data in, and then it calculates something and gives you an output. So the challenge is to get to this formula here. So the computation-intensive tasks are building the model. This, depending on the model, can take 10 minutes, can take an hour, can even take weeks if you use deep learning and neural networks. Applying the model afterwards in real time, as we will see, that's a fraction of a second sometime. So the compute-intensive part is where we build the analytic model, where we find this formula here. And this, in the end, why do we do machine learning? To build a simplification of the truth and to help you with decision making. Because the human cannot make all these decisions on these big data sets. And therefore, machine learning helps you with that. And they always help you with giving you a probability of making a decision. So typically, machine learning is not about saying yes or no, but saying about yes with 98% or with 95%. So machine learning is typically about giving you a good probability for something. The next step then is that you have to validate that your analytic model works. There are many different concepts which you can use here, and really you could, about each of these topics I show you here, you could talk probably a day about all of these topics on itself. But with cross-validation, for example, you simply use a historical data set and use some parts of the data to build a model and the other parts to test it if the model works with other data. And then you merge the data again and use other data to build the model and to test it and so on. And then you have your analytic model, then you execute it. And this is now where we come to the coding, for example, in Encoder also. This is also the live demo. One of the live demos I will show you in a minute. Here we have some R code, and in the R code we simply execute the build model. It's one line of code. And that's also an important lesson learned if most of you have not built an analytic model yet. Coding is not the problem in machine learning. So writing source code, it's usually a few lines of code. It's not like a typical Java web application or JavaScript where you have thousands of lines of code. So typically it's 10 lines of code, 20, 50, maybe 100, but it's not so that machine learning is very much coding. It's more about understanding the concepts behind that and playing around with that to find the right analytic model, to choose the right algorithm like decision trees, clustering, gradient boosting, neural networks, or whatever you want to choose. That's more the challenge. And therefore, there's this term data scientist, which they call, where you have a knowledge in mathematics and statistics, also in programming, and experience in all that. But it's not really like the typical developer who just writes some source code in the end. It's different requirements which you have. And on the other side, you can also execute the analytic model from a UI, like in the visual analytics tool, where the business analyst can make the decisions to if the model works. Because typically the programmer, the data scientist, builds the analytic model, but then the business analyst has to validate if that really works for the business case, because he has the domain knowledge about that. And before we come to the live demo, let's think a little bit more about the frameworks and tooling which we can use. There's a lot on the market. So typically, if you're just using a programming language, most people use R or Python. R is really built only for data science, so exactly for these cases, and Python is also very strong here. So that's when you want to use coding. And then you can use a lot of frameworks around that. For example, Apache Spark is used if you want to really scale it out to big data sets. You typically still use R or Python or maybe Scala to access the Spark cluster. But the computation is running on the Spark cluster where you can correlate terabytes and petabytes of data. Or use frameworks like H2O, which I will show you later, which has its specific advantages like very high performance, for example. And then what's coming more and more is deep learning. That's a specific subset of machine learning, which you might hear more and more. This is typically only about neural networks, which is one part of machine learning. And with that, you can do very powerful things, but it has also its trade-offs. For example, building a neural network takes much longer than a decision tree or so. So it has all its trade-offs, but it's coming more and more. And then we have also visual tooling. For example, the open source tools KNIME and RapidMiner. I will show you RapidMiner in a minute shortly to see how that works. This is if you do not want to write the code in R or Python, but use a visual tooling for that. And then there is many, many more. There's also standards for that, like PFA or PMML. So just to give you an overview here, there's a lot of frameworks, and it also depends on your problem, on your use case. So with that, let's skip this one. Let's go to some live demos to show you how that looks like if you build analytic models. So let me see. Here we are. So let's begin with some R code. Here you see a relatively simple example. This is 10 lines of code or so. And what we are building here is we are trying to predict churn of our existing customers. So we want to decide if an existing customer will probably churn in the future or not. And this is really the 10 lines of code which implement and use this analytic model. And first let's take a look at the data we have about customers. We have a user ID, and we already know about existing customers which churned, which is a 1. And if they are not churned yet, then it's a 0. They are still existing customers in our company, right? They still have a running contract or something like this. And if they are 1, they already left us and use another 1. So for example, a telco, they moved from Telecom to Vodafone, for example, right? Then they left, they churned. And we have a lot of other information about this, like the address, the gender, the frequency, and all this information. That's our historical data which we want to use to build an analytic model to predict for current customers if they will churn or not. Okay, so here we don't have a churn information. They did not churn yet, but we want to calculate if they probably churn in the future. And for that, we use a few lines of R code here. So here first, we read our CSV file. So this is more or less hello world. Again, if we want to use thousands of data sets, then we can use something like Hadoop or Spark. Here I just use a CSV file. And building my analytic model is one line of code. What I use here is the GLM. So typically, if you want to build an analytic model, you have a function in R, in Python, in Scala. And this is one operation which you use here, and it has some parameters. And here I say the attributes which I want to use for this for building this model are frequency and recency. So these are two of our columns here, because we assume, or because the data scientists found out that these are the most relevant to predict the churn. And we use these two to build the GLM model here. GLM, with that we can use things like linear regression, for example. So a relative simple algorithm for prediction, but it works here. And so in one line we build the analytic model, and then we apply it to new data sets. So here again we have our new data set where we don't know if it will churn. And now we can execute all of that. I already did that before, but it takes only a second or so. And then we see here in the, again, one line, we use the predict function of R, which is a generic function which you can use for all the different algorithms. And here we use it to apply our GLM model, which we built before, on the new data set. And then we get a churn probability out of that. And we use the last line here to print that or to add it to our table. So after we apply this analytic model to our new data set, we will see a new column here, which we see in the result data. And here now you see the probability of that. And this is what this analytic model gives us. This is a probability, and we have to validate if that works for our data. That's done by the data scientist. And then we can apply that. In this case of the telco example, we could decide, okay, the probability is very high that he leaves, so let him go. We can't do anything. If the probability is, for example, only 70 or 60%, we can decide to send him a coupon. So maybe he renews his contract if we send him a coupon or discount, right? On the other side, if it is 0.4%, we don't send him anything because the probability that he leaves us is very, very low. So we won't spend any money on him. And that's one example of how you build an analytic model and how you apply that then in a use case afterwards. Let's take a look at a few other examples. So this is what was one example with R. Let's take a look, for example, at deep learning. Deep learning with neural networks is very, very hype, and it's very interesting and powerful. But it has also advantages, like the building it takes very long. It also has some other disadvantages. But here I'm using the playground of TensorFlow. That's a web UI. Everybody can use it to play around and understand how neural networks work. And we have the same idea. We have historical data, and we want to use it to build an analytic model, in this case a neural network. to get insights about that and to train it how it works and to use it to predict for future events, right? And what do we see here? So this is not a specific use case, but relative generic data. And on the right side here, we see for this data set, we see either a true or false. Blue means true and red means false. This is historical data, and we want to then use it to predict for new data events if they are true or false. And as input here, in the first case, we use just these two here, which are colored, x1 and x2. And now if I click on play, you see here on the right side how it trains the model. It is a continuous training and backpropagation algorithm. I don't want to go into details here how neural networks work, but here this is training how the output should look like. And here now we see on the right side, in this case, this is pretty easy. So we have this line here, and all on the right side are blue, and on the left side are red. So that is pretty easy. So this model is running, but we could already stop it. This is one example, but now let's go to a more complex use case. So in this use case, as you see on the right, it will not be that easy. So if we try the same inputs here, the same x1 and x2, to train this model, we can run it forever. It does not work. So this is the wrong input information, the wrong features which we have here. This does not simply not work. So we have different options to change this model. So for example, we can change the input. We can give it more information here and try out if it works now. So we see it still doesn't work. So we can also change some activation functions. So this goes now more into the deep concepts of neural networks. But here, if we take another activation function, and also we can do things like changing the hidden layers, so we can do many things to play around, and that's typically what the data scientists do. They try with different algorithms and different configurations until they find something what works. Often it doesn't matter why it works afterwards. You have to find a model which works for your use case. That's the important thing. And if we try it now, you see it's building and training, continuously getting better and better and better. And here we see the error, the training loss is also reduced all the time, as we see here in very small. So here it's getting from 26, 25, 24. So this analytic model is getting better and better. And when it's good enough, then we can validate that it works with other data sets, and then we can apply it to new events to do predictions later. But here again, now we are training it a little bit too much. So because what we are doing here is we are overfitting. That is a term which means that we are training explicitly on this test data set, and we can't apply it to new events which have different information in it. So here again we use different configurations. So for example, regulation rates. And again here it goes into concepts of deep learning. But if I run it now again, then it will not become as good as before. And it takes much longer, as you will see here, until it gets better. Because I configured it so that it does not overfit too much. So that I can apply it afterwards also to new test data sets. So, and you can play around with that for an hour or two just to learn that and see how it works. And that's then what also the data scientists really do. Let's now take a practical example for this deep learning here. So let's stop this. And let me just check the time shortly. And so here, let's go to an example, a real-world example for deep learning. In this case, I use the autoencoder. Autoencoder is one example of deep learning. There are many others. And an autoencoder means, in the end, that you have a deep learning network where you have some input. This can be any kind of input. This can be bank transactions, this can be telco information, this can be any sensor information or whatever you have. And you put this into the neural network, and then you have an encoder, and you compromise the data. It gets smaller. And then you have a decoder, which makes it bigger again. And the goal of that is that you reconstruct the existing information with that. The basic example for that often is the picture example for autoencoders in deep learning, where you have pictures, and the first example, the first line here is the input, and the second line is the output, which you can see is very similar to the input, which is reconstructed, but it's a little bit different. And the reason that it's a little bit different is because we compress the data here so much. Right in the middle, so you cannot reconstruct it to 100%, but maybe 95%, which is fine here. This example here shows it how it works, but now let's think about a business case for that. And a business case for that is anomaly detection, where you again have a lot of input data. Again, this can be bank transactions or this can be telco information, and you want to find anomalies. And the autoencoder can be used here in the same way as I showed you in TensorFlow before. So I define how many iterations you do, how many hidden layers, which activation function to use, and all these things. And after you have configured your analytic model, you build it here, you create the model, and then you can apply it to data sets. And here is one example of that. And here the autoencoder is used. You have an input and you have an output. And you see the anomalies of that, because the autoencoder can reconstruct most of the information, as you can see here. But for one of them, you see here is an outlier. For this outlier, we have a reconstruction error, which is much bigger than for the others. Here it's 0.38, as we can see on the bottom right. And for the others, it's much lower. And with this kind of deep learning, you can use it to find anomalies. And anomalies can be fraud in bank transaction, for example. So you would simply use all your historical data about bank transactions, put it into an autoencoder deep learning network, and it by itself learns which are anomalies. And then the business analyst can take a look at that. Or what we use it in telcos for is, in telcos we see spikes in the telco network here. And often it happens that the telcos have some spikes, and afterwards they have an outage, maybe 1 week later. And with these spikes you can predict that you will have an outage in the network, and with this help you can replace the parts in the network before it actually breaks. And these are examples where you use autoencoders and deep learning to do that. And there is many, many more use cases for that. As last example here, I also want to show you RapidMiner. RapidMiner is if you do not want to write, or let's go back because here I haven't shown you the code. But in this case, I used visual analytics so that the business analyst can use it. But under the hood, I use coding, of course, here. And what I'm doing here, I use H2O libraries, which implement that. So this was built by the data scientist and incorporated into the visual analytics. And if you take a look at the code for building the model, it's again a few lines of code. So it's not the problem to write the code, it's really to understand it. And it's only a few lines typically. And here you use H2O deep learning to build exactly this autoencoder which I just showed you in the visual coding. And now if you don't want to write the code, or if you're not that experienced, you can use a tool like RapidMiner, which I use here, or KNIME. These are open source tools which you can use to visually do the same like with R or Python. And here I have one example where I use a Titanic data set to build analytic model, here again with deep learning, as you see. So first I use my deep learning component, and again I configure the hidden layers, the activation functions. And then I also do some testing and validation with that. And that's basically what you can do here for all the other things. So you can use the same for decision trees or for whatever algorithms are available in the tool. And the benefit is, especially if you want to getting started with machine learning for understanding the basics, these two tools can help a lot. But of course you also have to understand more details afterwards. So this is how you build analytic models. That's in the end, the most important step, because it doesn't help to bring them to action afterwards in real time if they don't work well. So you will spend most of the time on building and validating the analytic models first. And then you apply them to real time, which is then the second part of that. So if we go back to our analytic pipeline, you see here it's really just one part of the big process here. You deploy the existing model. And if you think about an existing model, really, and in the end, it's just a binary or a string which the data scientist creates, and you can reuse it afterwards. So let's take a look here. This is a typical real-time streaming engine where you have data ingestion, where you have input from new sensors, or maybe social media data, or whatever is the input data. And then you have things like transformations, where you do things like filtering or enrichment. And then just one part here, which you see here in red, is applying the analytic model. So event processing exists for 10, 15 years, or complex event processing, streaming analytics, however you call it, where you really act on a new event while the action is happening. And here now the new thing is that you can now also apply these analytic models which we built before to every single new event in real time to apply it here. To predict if it's fraud, for example. If a credit card transaction is done, you can decide in milliseconds or even faster if it is probably fraud. And this decides then, do we allow that transaction or do you have to call your bank to allow the transaction? Here again, we have a lot of different frameworks and products for that. So open source is the typical stream processing frameworks. Probably the most up-to-date ones are things like Apache Flink, Apache Apex, or even Kafka can be used with Kafka streams in the meantime. Or you also have, of course, a lot of commercial things. So I, in a minute, will show you TIBCO Streambase. The difference, these are more really complete environments where you have visual coding with testing and all these things. And it has all their trade-offs. What's now important is the question, how do you apply the analytic models to real-time processing? And therefore, you have to think about this at the beginning of the process, and not just now when you want to apply it, but before. We had many customers which built great analytic models with Python, for example, which really work to predict for fraud detection or predictive analytics. But afterwards, when they wanted to deploy it to action, they couldn't do it because it didn't scale as they needed. So you have to think in the beginning of how much do you want to scale it out and how performant should it be. And therefore, some tools then are better than others or some frameworks. And this is the reason why I show you in a minute H2O, which is one open source framework which is really built for very high performance. On other sides, R or Python alone are okay if you don't have to execute it a few thousand or even million times in a second. So that really depends on the use case. But what's very important also here is you do not want to redevelop the model, because if you use just Python first, but it does not scale for your use case, and then you rebuild it with other technology like Java to scale better, then you have the whole development lifecycle with validation and testing twice, and that doesn't make any sense at all. But we have seen that in the past at customers. So how do you apply it to real-time processing? It's not really complex. It's just a small part of the streaming process, as we have seen before. Here's one example where we built some analytic model with Apache Spark machine learning library, and then also apply it to Spark streaming. So that's a good combination then. Or you can also use PMML models, which is a XML standard. So you can build it with one tool and execute it somewhere else. This is just one example here how you code it. It's just a few lines of code again. Coding is not the problem here. It's really understanding the code. The same looks like if you use Kafka streams or if you use Apache Flink. That's some lines of code and you add it to your stream process. And the same is true if you use a coding tool, like I will show you in a minute, TIBCO Streambase, where you have visual coding. So here in the end it's one component. Like here we have a component where we use R and we just add the R binary to our stream process. Or the same for H2O or any other technology which you want to apply. Let's think about a use case I want to show you, because here I selected a use case where it is important that it scales and performs well. So here in this example, just Python or R would be the wrong choice because it does not scale in the case we needed it here. And this is predictive analytics for manufacturing, where we decide in an assembly line to scrap a part as early as possible. Because you can see here, in every station, station 1, station 2 as an example here, it costs money to do the work on every single part, right? And therefore you want to decide as soon as possible if you want to scrap the part. Because if you do scrap it later, it costs more money. And here we want to apply machine learning on each station to make a prediction. Do we want to scrap it, yes or no? So the analytic model helps me decide, do we scrap it in station 1, yes or no, and then we scrap it here or not. In the past, this was done just by some other analysis of the researchers, but without machine learning. And there, they asked us to do it with machine learning and also, of course, prove that you save money with that then. So if you take a look at the infrastructure, it's not really something special. In the end, you have the two parts I described you first. On the bottom, you see the big data store. In this case, it was Apache Hadoop, where the sensor information was stored, the historical data, where we find insights and patterns. Here we used visual analytics with TIBCO Spotfire in combination with R and H2O to build the analytic models. So this here is the first part. We built the analytic model. And when we have built and validated it, we deployed this H2O model to real-time processing. So this is our event processing components, where we apply every single new event. So in the assembly line, we have new input events, which can be whatever the sensor sends us. And this goes into our stream processing, and one part here is applying the analytic model in real time in that. That's the two parts in the end I described. The bottom one is building the analytic model, and the upper part is applying it to new events. Here's just one screenshot of our model which we built, so that we prove to the customer, hey, okay, based on your historical data, we can use the following model to save this and that money. And here you see we use two different analytic models. We used a random forest model of H2O and a GLM, linear regression, and calculated how much money you could save in the complete process if you apply these analytic models instead of not applying them. And for one assembly line with the random forest models, we could save 97,000 euros here, so around 30% of the cost. And therefore you see it's really big business cases which you can use here. And now let's take a look at that too, how that looks like. Again, I use H2O here. The same is true for any other technology or model you want to apply. The question is really more how it scales and performs in the real world then. So I already have the process running. What you see here, I don't want to go into much detail of the process itself, but the process does a lot of things. At every station in the assembly line, you get an input event. In this case, it was an XML message, which is pretty big for sensors. So you have to parse the message, you have to filter things, do aggregations, transformation, whatever you typically do in this real-time process for sensor processing. And just one component of that, which I want to focus on now, is the applying the analytic model here, which is the run H2O component here. And you see in the end what I do, I really just apply it here. H2O compiles to Java code. That's why it's so fast, as we will see in a minute. And a huge advantage compared to Python or R. And then for this H2O component, which we see here, you have inputs. Inputs is the pressure information which you have here, the different sensor information. This is sent to the analytic model, and then the analytic model applies that to give you an output. And the output here is the so-called score, and the score contains the probability, the prediction, to decide, do we scrap the part or not? And that's used for every single event in every single station, right? And now I have already deployed this, so let's take a look at the live UI for that. Here you see every point is one event, and you see that blue is if it's not scrapped, because it's under a threshold, which we defined as 0.5. And every prediction which is over 0.5, we scrap it. That's the yellow one here. And what's more interesting here now is to take a look at the measurements also. Because here it was really required to do it high performant. And if we take a look now at the measurements, we see here that the total process, in this case in average, takes 9 milliseconds. That's the complete process, including XML parsing, transformation, aggregation, and applying the analytic model. And if you take a look just at the model, which is the blue one, the model takes 0.3 milliseconds to apply. That's 300 microseconds. And this is not even optimized for performance. This was just in a proof of concept. But here you see that this is really high performance. And based on that, you have to really decide before which kind of technology you use for machine learning or deep learning. So with that, I'm almost running out of time already. But I'm also almost done. The last point, which is important now, I discussed a lot about building analytic models and deploying them to real time. Of course, in reality, this is then also a closed loop. So after you have deployed your analytic model, you still have to validate again. Does it still work? Like the spam detection in the beginning or fraud detection. Spam or fraud change all the time, so you have to validate it again and you have to train your model again. So this is really a continuous loop where you rebuild your model, you improve it and deploy it again and again. In some very, I would say, perfect situations, you really, even with every single new event, you improve the model. So that's, for example, what Netflix is doing when they have their recommendation engine, what movies you want, it recommends to you. On every single event, they in the end build a new model with that or continuously improve that model. That's the best case, which again, typically just the tech giants have today, and the other enterprises slowly go into that direction. But for many use cases, it's also fine if you rebuild the model every month, every week, or whatever the use case is, right? So in most use cases, it's not necessary to train it very often. And often you have models like in deep learning, where building the model takes a week already. And there maybe you do it every 6 months, right? Because that's also very expensive. Of course you can scale it out on Amazon or Microsoft or Google, but that's really then, it's not about hundreds of euros, that's about much more what you pay then for these calculations. Okay, so that's more or less it. So let's close this up with the key takeaways. So the insights are hidden in historical data. First, to find insights with machine learning, you need historical data. With that, you build analytic models. That's the most important thing to understand, otherwise it will not work. First, take a look at historical data and use machine learning algorithms, whichever makes most sense. Decision tree, clustering, neural networks. Try out different ones and play around with them, what works for your use case. And afterwards you apply to real-time processing and really without redevelopment, that's the key. So you have to think about this in the beginning, how much do you have to scale it, how performant has it to be, to deploy it in real time later. And we're already out of time, unfortunately, so if you have questions, please come to me back afterwards, or I'm also happy if you connect to me on LinkedIn or Twitter or so. And thanks for listening.